Welcome back. Here we're covering section 2.5, section on sets and compound inequalities. We're going to start with a little geometry review, concepts of union and intersection, which will play into our and or type homework problems tonight. Union, if you remember, everything must be represented with union. So union, you must include all the items in all of the sets being evaluated. Whereas intersection is overlap. Okay, where two streets meet, the intersection of 35th and Wisconsin is just one small area. But we're talking overlap, so common to the sets being evaluated. Okay, it's got to be in both sets or all the sets. So intersection, think overlap. Where union, everybody gets represented, like in a teacher's union or a machinist union that represents everyone. Okay, so a couple examples. I've got a couple sets down here. We've got set A and set B. Okay, set A is made up of numbers 1, 2, 3, 4, and 5, while set B is made up of sets 3, 5, 6, 7, and 8. Set B is made up of those numbers, 3, 5, 6, 7, and 8. Tell me what's in the set of A union B. So this U is the symbol for union, and the other example is A intersect B. So the upside down U is intersection. So the question's A union B. What is in A union B? Well, it looks like A union B is everything that's in A and everything that's in B. So the union are the numbers 1, 2, 3, 4, 5, 6, 7, and 8. So every one of those numbers makes up the union of those two sets. Whereas the intersection, that's a little different. The intersection is the overlap of those two sets. Okay, so the overlap is just 3 and 5. So the intersection of set A and set B are just the numbers 3 and 5. So if we're going to be solving inequalities with and, we want to solve each inequality individually. Okay, so we might have a couple of problems or 3 problems. We've got to solve each individually. And then we need to determine the intersection, the overlap. Okay, and then we give the solution, and that solution must satisfy all the inequalities. Solving inequalities with or, we want to solve each inequality individually again. We want to determine the values that will satisfy at least one of the inequalities. Okay, so that's the difference between and or. And it has to satisfy both or all of the inequalities. Whereas or, you only have to satisfy one. My favorite example of and or, let's say James and Joe are screwing around in class, and I've had it up to here with those two guys, and I say, okay, James and Joe, go see Mr. Kowaleski. Well, they both know that I'm not happy unless both guys go. Now, what if I said, got real angry, but I said, James or Joe, go see Mr. Kowaleski? Well, do they both have to go? Of course not. I'm happy if just one of them leaves the room. So that's the difference between and or. If I say James or Joe, well, James is going to point at Joe, Joe's going to point at James. I'm not going to go, you go. He's happy if just one of us leaves. So let's go ahead and get into the sample problems here. Let's solve these samples. Let's take a look at our first one here. It's an and. It's negative 3x minus 2 is greater than 5, and 5x minus 1 is less than or equal to negative 21. So let's go ahead and solve the left side first. I will go ahead and add 2 to both sides, and we get negative 3x is greater than 7. I want to solve for x, so I'm going to divide by negative 3. Oops, I'm dividing by a negative. So if I'm dividing by a negative, I'm going to have to change the direction of that inequality. I'm going to flip that inequality around and get x is less than negative 7/3. Let's carry through my and. It's an and problem, so I want to make sure I bring that down. And then let's go ahead and solve this particular inequality. The one on the right, add 1 to both sides. We get 5x is less than or equal to negative 20. Divide by 5. And we get x is less than or equal to negative 4. Okay, let's go ahead and graph these. And let's take a look at what our final solution is going to be. Okay, my important points here are negative 7/3 and negative 4. So let's go ahead, we'll put those on the graph. We'll put negative 4 here. We'll put negative 7/3 there. So I want all the x's that are less than negative 7/3. I'm not going to include negative 7/3, so I'm going to do the parentheses, and we'll graph that in red, and those are all the x's that are less than negative 7/3. Now let's graph all the x's that are less than negative 4. Well, again, less than negative 4, do my parentheses, and it's everything to the left of negative 4. Well, this is an and problem. So I want everything that's both red and green. So, anything over here, 0 isn't going to satisfy. That's not going to work for either of them. Something like negative 3, well, that's only going to work for the red. That's going to work for the one on the left. So the only thing that satisfies this is everything to the left of negative 4. So our final solution then is the solution x is less than or equal to negative 4. And in interval notation, that's everything from negative infinity, less than or equal to, so our parentheses, negative 4. Let's go on to sample problem number 2. Let's take a look at this. X plus 2 is less than 5, and x minus 10 is greater than 2. Another and problem. I'm going to add 2 to both sides, and I get x is less than 7. And I will add 10 to both sides, and I get x is greater than 12. Okay, so let's take a look at our graph. And we'll put our critical points in. Our critical points are, oh boy, I made a mistake here. I'm going to go back and correct my mistake. I don't want to add 2 to both sides. I want to subtract 2 from both sides. So, you guys probably all saw that. So I get x is less than 3. And x is greater than 12. So I have critical points at 3 and 12. I will go ahead and graph x is greater than 12. That's going to be an open parentheses, and I want everything to the right of 12. And I want x is less than 3, another parenthesis, everything to the left of 3. So I want numbers that are less than 3 and greater than 12, and you've been going, hey, there are no numbers that are less than 3 and greater than 12. So there are no numbers that are both green and red. Nothing satisfies. So this particular answer is no solution. Let's take a look at sample problem 3. This particular one is an OR problem. Okay, so we've got our OR, and let's solve the left-hand side, then we'll solve the right-hand side. So we'll subtract 1 from the left, we'll get negative 4x is greater than or equal to 8. We have to divide by that negative 4. Okay, so we divide by that negative 4, which means we have to change the direction of that inequality. So we get x is less than or equal to negative 2. I'll carry my or down so I remember what kind of problem it is. And let's go ahead and solve the right-hand side. I'm going to subtract 3 from both sides. Get 5x is less than or equal to negative 15. Divide by 5. X is less than or equal to negative 3. Let's go ahead and graph our solutions. Let's see what we're working with here on our graph. So if we have x is less than negative 2, I get critical points at negative 3 from the green and negative 2 from the red. Let's go ahead and graph that. X is less than or equal to negative 2, so parenthesis and everything to the left of negative 2. X is less than or equal to negative 3, so everything to the left of negative 3. It's an OR problem, so I want numbers that are less than negative 3 or less than negative 2. So, go ahead and ask yourself, are you happy with 0? Well, no, that's not going to satisfy either of them. It's an OR problem, so I only have to satisfy one. Am I happy with negative 2.5, something in here? Sure, that'll work. Am I happy with like negative 5 or negative 10? Yeah, that'll work. So our algebraic solution is x is less than or equal to negative 2. And our interval notation tells us that we're going to go from, pardon me, we're going to parenthesis there, negative infinity. And we're going to start at negative 2, and we're going to be happy with negative 2. So that is our interval notation answer. And finally, on to sample problem 4. Another OR problem. We'll solve the left-hand side first. I'll subtract 5 from both sides. So we get negative 2x is greater than or equal to 6. Divide by negative 2. We get x is, almost got me on that one. Change the direction of the inequality. X is less than or equal to, we divide it by a negative, negative 3. Or, bring that baby down, and add 7 to both sides on our problem on the right. So solving our inequality on the right, I get 4x is greater than or equal to 20. Divide by 4. And I get x is greater than or equal to 5. Let's go ahead and take a look at this. I want x's that are less than or equal to negative 3. So I got a negative 3. I want x's that are less than or equal to negative 3. I might as well use red. So that's going to look like that. I want x's that are greater than or equal to, lost my negative sign, are greater than or equal to negative 5, negative 3, and critical points at negative 5. Okay, so negative 5, negative 3. I want x's that are less than or equal to negative 3. I want x's that are greater than or equal to negative 5. Good. So now this is an OR problem. Let's take a look. So I want anything that's green or red, don't I? So am I happy with 0? Sure, that's in the green. That'll satisfy the inequality on the right. Am I happy with -10? Yeah, that'll satisfy the inequality on the left. And of course, something like -4 would satisfy both. So I'm happy with any one of those particular scenarios. So it looks like we've just covered the whole number line. So our final solution is all real numbers. That fancy R is all real numbers. And in interval notation, we're just going to go from -infinity to +infinity. That wraps up section 2.5 on sets and compound inequalities, and we'll see you guys in class.